Howdy, students. This is Chapter 15, Lesson 3, and this is going to cover a weak acid, strong base titration. And what we're going to do is plot 6 points along the addition of a strong base addition to a weak acid. So I would have a calculator handy, possibly a highlighter as well as we plot these points. Okay, so let's go ahead and start by looking at a weak acid, strong base titration curve. And we can kind of note some differences between the strong acid, strong base curve. So the first thing I'm going to notice is that our pH to begin with from a weak acid is not going to be closer to 0 or 1, but we're going to start at something like 3. Now, it doesn't always have to be 3. But what we're going to notice is there's going to be a slight sharper increase, but then there's going to be a leveling out portion right here. And that's going to be a longer point, and we're going to have this buffering zone. And then what's going to happen is we're going to enter this sharp point in the curve, but it's not as sharp as the strong acid, strong base. And we're still going to find our equivalence point in this region. And then what it's going to do is level out when we hit the strong base. And again, the equivalence point here is 9. It's going to be in the basic region above 7. But it doesn't have to be 9, but it is going to be in the base region. Okay, so we're going to assume that this is going to go to completion. But before the equivalence point, the concentration of the weak acid and the conjugate base can be determined. So halfway, this is going to be special, but about halfway to the equivalence point, we're going to get the pH, and that's going to be equivalent to the pKa, and we can actually relate that back to the Henderson-Hasselbalch equation because the concentration of the conjugate base in the acid will be the same. At the equivalence point, a basic salt will be present, and the pH will actually be greater than 7 because the basic salt is going to produce hydroxide in solution. So there's going to be a strong base dominant after the equivalence point, and so the pH is going to go above 7. So let's go ahead and jump into our weak acid, strong base titration. The first point asks us to go ahead and chart the first point where there is no NaOH been added to our solution. We have 25 milliliters of a 0.1 molar acetic acid solution. Now, when we're reading the problem, you have to sometimes take a step back and look at the bigger picture. This is a weak acid and a strong base. You have to identify because that's going to change the trajectory of everything else that you do for this problem. So what do we know about this problem? Well, we know that we're going to have to exclude sodium hydroxide. So the first point can be taken using a Rice table because acetic acid is a weak acid. So remember that in a Rice table, we use concentrations. We're going to use a Ka expression because the weak acid is dissociating. And because we have H plus concentration, we're going to have to use a Ka value. My initial concentration of acetic acid is 0.10 molar, 0 H plus to begin with, 0 acetate ion dissociated. Here is our minus X plus X changes in our equilibrium values. Now, the acetic acid Ka would have to be given to you, but here it is, the Ka value. X squared on top, 0.10 minus X on bottom. This is negligible. So let's refresh. We're going to have to, there is no common ion, right? This is not a buffer solution. We're going to have to cross multiply and take the square root. So be careful while solving. It's been a while since we've square rooted something. We're going to get the H plus concentration. From there, we can get the pH. Now, is this reasonable? Yeah. A pH 2.87, it's not the strongest, but it's not the weakest. So we're going to be right in the middle there. Let's plot our first point at 0 addition of NaOH, pH of 2.87. Now, this is going to be, I'm going to kind of fix this dot. It's a little bit off. But there's roughly our first point. Okay, let's go ahead and move on to the second point. Okay, this is the step that we are going to really get into it. So we're going to calculate the pH of the solution after 5 milliliters addition of a strong base to a weak acid. And then we're going to add this point to the graph. So here we go. This is what we've been working towards. Okay, I am adding a strong base to a weak acid. Acid plus base is a forward-facing arrow because we have an actual chemical reaction. And if we have a chemical reaction, we need a BCA table. That's right. So let's go ahead and calculate moles of all of our substances that we have. We have 0.0025 moles of H plus to begin with. Okay. And then we are going to be adding, using the strong base, 5 milliliters, which I turned into liters, 5.0 times 10 to the negative fourth moles of hydroxide being added to the H plus. Okay. So what type of reaction do I need to write? Well, if I have OH being added to the solution, what I need to calculate is the amount of weak acid and conjugate base that is remaining after the addition. So I'm going to plug in my values for the weak acid, and I'm going to record and write in the values for the hydroxide. Water we do not include, and currently there is no conjugate base, the acetate ion. We're going to continue with a minus of our limiting reagent, and in this case, hydroxide ends up being our limiting reagent. And the hydroxide will be completely consumed at the beginning of this titration. So we go down to 0. There is some weak acid remaining. And then on the right side, we have added some conjugate base. That's interesting. That is going to play a factor into how we continue with these titration points. What we have is a weak acid and a conjugate base. So currently, this is a buffer. And also, I want to go ahead and have us write in the general equation. For a strong acid, strong base, we had H plus OH minus yields water. But in this case, what we have, and this is how we were able to actually write the reaction for the BCA table, we have an aqueous solution of acetic acid, a weak acid. This does not dissociate, so we don't write H plus. We're going to add that to OH minus because that's what the strong base adds. And then we're going to form H2O, and I'm going to squeeze it in here, the conjugate base A minus. So if you were wondering why we didn't include H plus, it's because weak acids in this case are going to be meant to be written without being dissociated. Okay. A Ka value was given in the first part of the problem. So because we were given a Ka, we can go ahead and use a Ka expression. So this is the point where students get kind of confused. They don't know what to write for the rice table. You got to use whatever is given to you in the problem. So in this case, we have a Ka. We can write a Ka. So here's the acetic acid in equilibrium with the H plus the acetate ion. So let's go ahead and plug in our values. Now, remember, rice tables work with concentration while BCA works with moles. So make sure you're dividing moles by liters. And we didn't show that work here. We took 0.002, divided it by 0.067. 0 for the H plus. And then we took this and divided it by the liters of solution, which was 5 milliliters. Equilibrium is going to shift to the right, minus x plus x plus x. Here's our equilibrium values. And then from here, we can solve using our Ka value. We have 2 negligible x's. Why? Because this is some sort of buffer. And you'll see that pattern when we have buffer systems. We're going to cross multiply, taking out those negligible x's, and solve for the H plus concentration. And then once we get x, and we have the H plus, we can take the negative log to find the pH, which is 4.15. Now you'll notice this is different. Strong acid, strong base, we had a small increase in pH. But here there's kind of an initial jump from no base to adding a strong base. We've entered the buffer region, though. So let's go ahead and plot our point. Clear up some space here. Okay, there's the first one, and here is the second one. All right, this point we want to calculate the pH of the solution after 12.5 milliliters of NaOH have been added. And this is a really special point, and we're going to see why in just a moment. So we are going to add base. Okay, we're going to start out with the concentration of weak acid to find moles, which is 0.0025 moles of H plus. And if we are using the BCA table, then we're going to be using the acid form. Here is the amount of moles of sodium hydroxide that I'm adding. My BCA table is going to be acetic acid plus OH yields H2O plus the conjugate base. Remember, that's the general form when we have this type of titration. So I'm going to plug in the moles. Here is moles of weak acid, moles of OH, pure water, and then no conjugate base right now. Remember, we are assuming that we're starting fresh every time on these points. So don't get confused trying to go back and recalculate the volumes and what have we added and what's the pH. And no, we're just going to assume that we started from 0 milliliters of titrant. The change, our hydroxide, if you look at the values, is still limiting, right? 10 to the negative third. That's still going to run out first. So hydroxide is going to go to 0. We're going to have some weak acid left, but we're also going to have some conjugate base. Now look at this. Hydroxide is used up. I want you to box this in and note this when you're writing in your notes. This is huge. The amount of moles of acetic acid and the amount of moles of the conjugate base are equivalent. So real quick, I'm going to make a note, and I'd like you to write this in your notes as well, maybe off to the side. But if we have a Ka expression, the generic expression for the dissociation of a weak acid is H plus times A minus products over reactants. At this point, if we were to actually calculate the concentration by dividing by liters of solution, what we would find is that these two are going to cancel out because they have the same value, which means Ka is equivalent to the H plus concentration. And what we can also do is go ahead and do a derivation. If we take the negative log of both sides, we know that the negative log of the H plus concentration gives us the pH. And if we take the negative log of Ka, that gets us something called the pKa. Okay, so this gets us to a point at which we call the half equivalence point. When we have a perfect buffer solution, same concentration of acid, weak acid, and conjugate base. So I'm going to erase this. Let's continue on. Make sure you have this in your notes. We could do a rice table here, but what you're going to find is that because these amounts are equal, the pH can be calculated directly from the Ka value. So let's take the negative log of the Ka value, which was 1.8 times 10 to the negative fifth, and we are going to solve for the pH of 4.74. And you'll notice that that jump isn't very big. So if we plot our points, 1, 2, the third one is actually leveling out, and it's not actually going a whole lot. Remember, this is a buffering zone within the titration curve. So really important point, and I want to talk a quick bit about what could be asked here. At the half equivalence point, we can figure out the volume of titrant that was used, and we can figure out the pH here, which would tell us the pKa. And if we take 10 to the power of negative pKa, what we can find is the actual Ka value. And from the Ka, we can do other things with that as well. So there's a lot of information that can be found from this point, and the AP exam loves to ask questions about this magical place on the curve. Let's move on. Okay, let's continue on. Calculate the pH of the solution after 20 milliliters of NaOH. And by the way, the half equivalence point was 12.5 milliliters of NaOH. So you can basically guess what the equivalence point will happen. So it appears that we may not quite be at the equivalence point, but let's keep going. There is addition of NaOH, which means we will be entering a chemical reaction, acid plus base, which means we'll need a BCA table. The amount of moles of the weak acid is still present. We're changing the amount of moles of OH because we keep adding more. We're using the generic equation for a weak acid strong base titration. We're going to plug in, and OH minus is still, I'm going to write it in, is still the limiting reactant. We subtract and add. We run out of hydroxide. We have a little bit. You'll notice this is getting smaller here for the weak acid. A little bit left, and we are producing more and more of the conjugate base. Only HA and A minus are left, so we're going to use the Ka plus. We had the Ka to begin with. Our rice table, we are going to use the Ka expression for a weak acid. We're going to plug in our values, and remember, there is no hydroxide, so we can get away without using a Kb expression still. Seems like that may change after the equivalence point. Remember, this is concentration, which was moles per liter. Make sure you're keeping in account the total liters of solution. And then we can solve our equilibrium expression, taking out the negligible x's, cross-multiplying and dividing, which gives us the H plus concentration and the pH. Now, of course, pause the video if you still need more time, but let's go ahead and plot our points out. 1, 2, 3, and then our fourth one. And maybe this isn't the best, but it kind of levels out first, and then it looks like it's starting to go up again. So I know that looks kind of linear, but there's this kind of buffer zone, right? Keep that in mind. Now we're going to calculate the pH of the solution after, here it is, 25.0 milliliters of NaOH has been added. And remember, 12.5 was the half equivalence point, so perhaps we have indeed reached the equivalence point, but let's go ahead and solve it and verify that that is the case. So what do we have? Well, 25 mils, same amount of moles of weak acid, and we're going to have even more NaOH, so it's contributing even more moles of hydroxide ions. This is a forward-facing arrow BCA table. We're going to throw our moles in here. Now, this is where things are going to start to change a little bit, right? Let's look. Now, the hydroxide is being consumed, and it is our limiting. But what you'll notice, and I don't know if you actually picked up on this, but 0.0025 is 2.5 times 10 to the negative third. So both of these go to 0. And doesn't that make sense? The equivalence point, I'm going to put this, equivalence point is when the hydroxide neutralizes all of the H plus ions that are being donated to solution. So what does that mean? But it's not at a pH of 7, right? We kind of looked at that curve. So we have conjugate base. And remember, this is from a weak acid, so it is a strong conjugate base, which means it's going to attack the water. Only A minus is left, right? The conjugate base. So we're actually going to be producing hydroxide, which means we're going to need a Kb expression to show the hydroxide formation. So here we go. This is different. Look at how I'm writing this equation. The acetate ion is going to attack water, ripping off a hydrogen, forming the weak acid, acetic acid, and producing that hydroxide ion. Really got to be careful here at what's happening. So the initial, remember, this is molarity. We need moles per liter. We're going to plug that in for the conjugate base. And where is that coming from? All the way over here. So we're not just willy-nilly plugging in things like we used to. We got to make sure we keep track of what's happening. Okay, zeros on the right, our equilibrium will shift to the right, minus x, and we have 2 plus x's now. We're going to have an x squared. Remember, we've been working with a Ka problem, so we have to convert into Kb. Just a quick refresher, Kw equals Ka times Kb. So we need to solve by taking 1.0 times 10 to the negative 14 and dividing it by the Ka in order to solve for the Kb. So that's where this 5.6 times 10 to the negative 10, that is a Kb value. We're going to get rid of this negligible x, and we're going to cross multiply and solve, but be careful. Remember, the x value is no longer H plus, it is OH minus. So if we're solving for pH, remember, we may need to find the POH first and then find the pH. Now, look at this, 8.72. That's above 7 at the equivalence point. So let me make some space here. See what's going on with our graph. Here's our points. 1, 2, 3, 4, 5. It started going up, and then boom, look at that. And if I'm drawing this out, remember, it goes up. We got our buffer zone, and then shoot, up to the equivalence point. All right, let's continue. And excuse me, before we move on, we are going to also ask you, why is it not at 7? All of the base has been consumed, all of the hydrogen has been consumed, but because we have a strong conjugate base, it adds additional hydroxide ions, which is why at the equivalence point there is a basic pH. Okay, let's go ahead and plot our last point. We have reached the equivalence point. It took 25 mils. Now we're adding 40 mils of NaOH, which is way past the equivalence point. So let's go ahead and see what happens. Remember, we're still adding acid to base, so we still need to calculate our moles of acid and base. We need to set up our BCA table using the same weak acid to hydroxide equation. We're going to plug in our moles of H and OH, and what you're going to find is that now is the time when acetic acid becomes the limiting reagent. And so what we have is 0 for the acid, and we have a concentration, or excuse me, I keep using concentration, I apologize. This is moles. We have moles of hydroxide and moles of conjugate base. We could go ahead and do a rice table and figure out how much hydroxide the conjugate base is adding. But what I want to emphasize here is that the concentration of hydroxide is really going to be the major influencer of pH in this problem. So we don't really have to keep count of what's going on with the conjugate base. We can simply take the concentration of hydroxide, and remember, that's moles per liter. So you'll see that these numbers are different. And then we can find, of course, the POH from there and get the pH. Look at this spike. Wow, of course, we're adding strong base. Makes sense that what would happen is it would hit the equivalence and then really jump. So again, I'm going to go ahead and plot this. We're going to have this buffer zone after the initial spike, and then we're going to creep up, and then boom, we've got our equivalence, not as sharp as a strong acid, strong base, but then boom, it's really going to go up there and level out as we hit that strong base concentration. Okay, and that's going to do it for a weak acid, strong base titration. Please ask your teacher if you have any questions about what's going on here. Y'all have a great day.